So let's relate electron configurations to the periodic table. Valence electrons. Valence electrons are electrons in the outermost principal shell, the principal shell with the highest principal quantum number. Okay, I'm pretty sure that made like almost 0 sense to you. Valence electrons are the electrons staying in the highest floor of the hotel that has any electrons staying in it. So on that previous example, what's the highest floor that has electrons in it? 3. The third floor. So how many electrons are staying on the third floor? 8. So we say that argon has 8 valence electrons. So we're looking at the hotel and we're looking at the highest floor that has anybody in it. How many people are staying on that floor? That's valence electrons.
Even when they fill in a different order?
Yes, even when they fill in a different order. Fine. Yes. I know. And the reason we care about this is that those valence electrons are the ones that are involved in chemical bonding. And the reason we're talking about this at all is so that we can understand how atoms interact with each other to form chemical bonds. It's the electrons that are farthest from the nucleus. Those are the ones that are on the outside of the atom, right? So you have 2 atoms getting together. Which electrons are going to interact? It's the ones on the outside, the ones that are farthest from the nucleus. Those are going to interact with electrons from another atom. That's where the hotel thing doesn't work so great, because you don't have 2 hotels like doing something, I don't know. The electrons that are not in that are called core electrons because they're more in the middle. So I think we need a picture. So I'm going to draw a little picture here using the Bohr model, even though we recognize that it's not correct. How many electrons could be on the first floor of the hotel? 2. So I'm going to make those dots. So there's the first level. On the second floor, what's the most electrons that we can put on the second floor? 8. The S room can hold 2, and the P room can hold 6. And so if they were all full, we'd have 1, 2, 3, 4, 5, 6, 7, 8. Which electrons are further from the nucleus? The 8. So these are more on the outside. This is not how they're arranged. It's not 8 electrons going in a circle, this big conga line or something, right? But it does correspond to how large those orbitals are. The second level, the orbitals are farther from the nucleus. And so we can draw a picture like this just to help us understand, yeah, these are the ones on the outside. And so if I have that atom, running into this atom, maybe this one has 3 electrons on the outside. These electrons are the ones that are going to be involved in the bonding. These electrons here are core. Where's the core of an apple? It's on the inside, right? These electrons are on the inside. So the highest occupied floor in the hotel, those are the valence electrons. All the lower ones are core electrons. I know.
I'm good with this.
You're good with this? Good.
I'm good with this, but my problem is, I thought the farther away from the nucleus, the higher energy. And so if it takes more energy to be 4D than 5S, then the 4D are farther away, and therefore the valence shell isn't 5.
I think let's not go into the wonky part yet. Okay, there is that weird order thing. It's there. It's kind of a foreshadowing. It's coming. We're going to have to deal with it a little bit. But let's not think about it yet. So if we ignore that part, are you okay with it? Okay. Anybody else have any questions? Because see, this is where the learning gets customized, right? I explain something, and then you're like, well, okay, but what about this? And then I change what I'm going to say to make it make more sense for you. But if y'all sit there like lumps, I'll just go on. That's fine. You can be lumps. I would prefer to be a lump myself. I'd like to be a lump in my bed right now, but not happening. Let's look at silicon. So here's the electron configuration for silicon. 2 plus 2 plus 6, there's 10, and 4, 14. We look at silicon on the periodic table, 14 electrons. So we've got the 1s, and the 2s, and the 2p, the 3s, and the 3p then only has 2 electrons in it. So we look at this and we say, well, where are the valence electrons, where are the core electrons? Well, what's the highest floor that has electrons in it? What's the highest energy level? It's 3, right? So we're going to look at all the electrons that are on the 3rd floor. It's a total of 4, right? There's 2 in the S room, and there's 2 staying in the P room. And so this has 4 valence electrons. I don't want to be blue. Be orange. Different. Okay? So there's 4 electrons there. Those are the valence electrons. They're the ones on the highest level. Everybody else below them, those are the core electrons. How many core electrons? 10. So here we have 10 core electrons. The valence electrons, okay, so I told you I'd tell you when things were really, really important and not so important. So electron configurations are important, but you could pass the class without getting a good handle on those. Identifying valence electrons is really important because that predicts all kinds of things. So identifying valence electrons is important. Okay, so let's write an electron configuration for chlorine and identify the core and the valence electrons. Well, how many how many electrons does chlorine have? 17. So there's chlorine, and it has 17 electrons. Okay, so let's start. 1s2, 2s2, 2p6, 3s2, 3p. How many am I going to need in the 3p? 5. If I add these superscripts up, they need to add up to 17, and they do. How many valence electrons? 7. It's these guys. The 3rd level, there are 7 electrons. How many core electrons? 10. So the highest big number, add the superscripts. That's the valence electrons. All the others below that are core electrons. What group in the periodic table is chlorine in? 7. Group 7A, or group 17. And it has 7 valence electrons. We just did silicon, right? Silicon had 4 valence electrons. What group is silicon in? Group 4A, or group 14. You think that's a coincidence? Not a coincidence. Okay, let's look at selenium. So selenium is bigger. Selenium does get up into the part of the hotel where the ordering is crazy. So we're not doing the electron configuration, we're just looking at it. Here's the electron configuration for selenium. Valence electrons. We're going to look for the highest floor in the hotel that has anybody on it, the 4th floor. The 4th principal energy level has electrons. Now, yes, the 3D electrons are higher in energy than the 4s electrons, but they're not considered valence electrons. And that may bother you. and we just have to get over it somehow. Okay, we're just counting on the highest level. So there's 4s2 and there's 4p4. 2 plus 4 is 6. There's 6 valence electrons. Because these guys are on the third level, even though they're paying more, they're still considered core electrons. It's the highest floor. How many electrons on the highest floor in the hotel? Those are the valence electrons. So valence electrons doesn't perfectly correlate with energy of the electrons. It's more, what floor are you staying on? Well, I'm on the highest floor that has anybody on it. Those are the valence electrons.
They do this because you can't have more than 8 valence electrons, right? And there's 10 in that 3D thing, so you have to fill the 4s first in order to not have more than 8.
Yeah, we're not going to have more than 8 valence electrons. And this is where it becomes very difficult to explain why. Because it comes down to these crazy wave functions and these very complicated mathematical functions and calculations of why does it go like this. And so I can't really give you a good explanation just because. Because Mrs. K said so, right? And would I lie to you about this? So, I do lie to you. Okay? In a beginning chemistry class, we have to lie to you. We have to make some generalizations and skip over some stuff because otherwise you can't handle it. It's like, the 5-year-old comes and says, where do babies come from? Do you tell him everything you know about how babies are made? No, because he's not going to be able to handle it, and he doesn't need all that information. So what we try to do in beginning chemistry classes is just give you the information that you need. Well, sometimes that doesn't always answer your questions, but to completely answer the questions, we'd have to go off and spend a lot of time on some other stuff that you don't really need to know about. Okay, so this is getting more towards my favorite part of this, bringing in the periodic table. So here are the first 3 periods, the first 3 rows of the periodic table. There aren't any transition elements on the first 3 rows. They start on the 4th row. So there's this little gap here. We cut off the bottom of the table, and then we just push these together. So here's from the left side of the periodic table, and these are from the right side. And here we have my favorite group numbers, 1A, 2A, 3A, etc., through 8A. Let's look at these electron configurations. And what they've done here, because there isn't room for everything, is we're just showing you the highest floor in the hotel that has electrons on it. So lithium would be helium plus 2s1. Beryllium would be helium plus this, right? Magnesium would be neon plus 3s2. What do these 3 elements have in common in their electron configuration?
One electron in the valence shell.
Yeah, they've got S1, 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 S1. And the level filled goes 1, 2, 3. This is period 1, this is period 2, this is period 3. What about these guys? There's S2 and S2. Well, why is this guy over here? Well, he's one of those little brothers, the tag-alongs, that get to bend all the rules. So when we're looking at this, we'd like to put him over here, wouldn't we? Because then we'd have, well, I can do that. I will put him over there. Put him right in here. There's HE, and that's going to be 1s2. 1s2, 2s2, 3s2. Isn't that nice? And here's boron. So boron's got the 2s2, and then that next electron goes into 2p1. Aluminum has 3s2, and then the next electron would go into 3p1. So these end in p1, p1, P2, P2, P3, P3, P4, P4, P5, P5, P6, P6. What these are showing is the valence electrons. How many valence electrons does lithium have? 1. What group is lithium in? 1. How many valence electrons does magnesium have? What group is magnesium in? How about oxygen? How many valence electrons? What group is it in? Argon, how many valence electrons? Group 8. And see helium? How many valence electrons does helium have? 2. It's in group 8. Well, he's so tiny he can't even have 8. He only has 2. So we've got these little, the first row, like I said, there's the baby brothers and they break their rules and we just have to excuse them because they're little and they're cute, right? So, okay, we'll let you do that. But the rest of them follow this beautiful pattern. This block, see how the periodic table sticks up over there, these 2 columns? How many electrons fit in s orbitals? 2. And then over on the right, over here, how many columns are there? 6. How many electrons fit in a p subshell? 6. So, was that the symbol for mind blown? Yeah. This is kind of mind blowing. So this is how I look at electron configurations. You're basically taking the periodic table and then you're counting and filling in. So if I'm doing nitrogen, there's 1 electron, there's a 2nd, 3rd, 4th, 5th, 6th, 7th. So this would be, let me draw numbers in here. This is period 1, period 2, period 3. This is the first floor of the hotel, and it's got that S room that can hold 2. There's 2 elements here. These are representing 1, 2 electrons. And then the second one, this block here is the S room, so this is 2S. And then over here, these are representing the people staying in the 2P room. And there's 1, 2, 3 for nitrogen. And so we can look at the periodic table and pull these electron configurations off of the periodic table, which I think is much simpler than drawing that diagram with all the arrows and stuff. So let's look at the whole thing now. So here it's color-coded. This is the S block. This is the D block. This is the P block. And then these guys down here would be the F block. We're not going to visit the F block. Question?
We're not going to do the D block either, right?
We're going to do a little bit of the D block. Just a little bit. We're going to do... Yeah, we're just going to do a little bit of the D block. Maybe just the first row. I can't remember exactly. But now the order goes like this. So here's 1S, there's 2. 2S, there's 2. This is 2P, there's 6 squares. 2P6, 3S2, 3P6. Next is 4S2. Okay, what about these guys? So I look at this and I see, oh, here we've got steps going down, and then, whoa, what happened there? It's almost like this whole section sunk down, right? And it looks like it should really be up here. Oh, that's the wrong color. I would like it to be up here. And then we'd have this nice dum-de-dum-de-dum, right? Except it isn't like that. But the sinking down thing helps me remember. I've got 4S, oops, didn't mean to do that. 4S2, this is the D block, but it's not 4D, it's 3D. It was 3, and there was a sinkhole or something, and it sank down. This is 3D. How many boxes are there? 10. How many orbitals are in the d subshell? Well, there's 5 orbitals. They each hold 2 electrons, so they can hold 10 electrons. So there's 3d. Now, this wasn't the sunken part, so we're back to 4. This is the p block. 4p, there's 6. And next is 5s2. Again, this is sunk. So this is 4d, 10, 5p6, 6s2. And then we're just not even going to talk about that. But basically, it's cut and pulled apart, and that one sank also. And we don't need to do that. Questions? Valence electrons is the main group element for the main group elements is the number of its column. Right? So 5A, all these guys have 5 valence electrons. We don't, it doesn't work for the transition elements, and helium, you have to remember, is an exception. Yeah, we'll finish that.